Wait for a few minutes. Wait for a few minutes. We set up the class.
A suspended uniform or meter rule in equilibrium when a mass of 50 was hung at the 0 mark. That is, so we have, it is suspended on a string, and then we had 50 mark, 50 grams here, which I said 50 grams, if you convert that one, you will convert to Newton. Then from here, that is 0 mark. This is at 100, and this is at 10 mark. So they're asking you to determine the tension on the string. The tension on the string. So that question was 3 marks in Form 3, and that is what we want to look at still on the moments. Now, this is at 10 centimeter, this is 0 centimeter, and this is at 100 centimeter. So this is a meter rule. It has no weight, so we are going to assume the weight is negligible, unlike the question that we did yesterday. Now, with that, we are going to change this first into Newton, and that is 50 over 1,000 times 10. We're going to get 0.5. So this is actually 0.5. That is going to be 0.5 Newton. So as usual, for us to solve this case, remember, moment can be taken from where the force is acting or at the end point. So like this case, we can take moment at this point because we don't have any pivot for such a case. We can take moment at this point, or we can take the moment at the end point, which happens to be this point. Now, the best point to take our moments, that I said the point where we are taking the moment, that is going to be the pivot point. So I'm going to take, because if I take moment here, if I take the moment where this force is acting, what I'm trying to do is like, I'm trying to eliminate this force, because its moment, it will no longer produce moment if I take it to be turning point, because it is going, if this is the pivot, it is going to cover 0 distance. So the moment is not going to be there. If I take this point, that means I'm eliminating T. So because I have only 2 forces, that means that I'll have to take my moments about this point here, the end point. So if I take my moment from this end point here, then I'm going to have, if I take my moment at that point, then I'm going to have my force 1 here, and I'm going to have also the tension acting there. I said always you treat one force and assume the others are not there. Assume there is no tension, and this is the turning point. This force is acting down here. We are going to have your body moving, or the moment moving counterclockwise. So the force is going to produce a counterclockwise motion. Assuming you cover that force, it is not there. So only we have this force. Second case is when we are going to have, now assume this force is not there, only tension is acting on the body. Tension is going to pull it up. So if it is pulling up, then this body is going to turn upward. So that is how we're going to have our moment. Now you can see, always when you have some forces acting in clockwise, the other must be acting in anti-clockwise for the body to be in equilibrium. So this case, we have this being counterclockwise moment, and anti-clockwise moment, and then this is going to be clockwise moment. So from there, we have those are the only two forces acting. So we always know that for a system at equilibrium, clockwise moment is equal to anti-clockwise moment. Then we are taking, now the clockwise moment is the force due to tension. Here, from where it is acting is a 10 mark, and for the pivot is at 100 mark. So it means from here up to the end, that is going to be 90 centimeter, which if you convert to meter, that becomes 0.9. So we're going to have the force, moment is force times distance. Now our force here is tension T, which we don't know, times our distance. It is acting at a distance of 0.9 meters. Everything has to be in meter and Newton. Should be equal to counterclockwise moment, which has a force of 0.5 times the distance. Now it is covering the entire distance. That is 100 centimeter. In meters, that is 1 meter. So from there, T is going to be equal to 0.5 times 1 divided by 0.9. And if you solve that out, now you're going to have your answer. That is the force, and it is going to be in Newton. So that is 0.5 divided by 0.9. It will give you the tension in the string. Okay? Now, we can also have such a question on moment, but now where three forces are acting. Let's take another case where we are having such a body. We are having a uniform meter rule. Let's say a uniform meter rule with force F. Let's make this tension, and then we have the force here at this distance. Let's say 0.5 Newton, and then we have another force here acting. So this force is acting down, this force is acting down, and then, sorry, let this force act up, and this force act up. So this is force T. We have this force as 0.3 Newton. Now the distance from the end here up to here, let's say it is 10 centimeter. The distance there, let's say 60 centimeter, and the distance up to the end there, let's say, now extend this a bit, you want it to add up to 100. So that is 70, let's say from here, this is 30 centimeter up to the end point there. Now we have this force here, which is acting from this side. It is at 40 centimeter, and at this point, it is 60 centimeter. Now we have such a case, and we are looking for the force T, or the tension T for the moment. Now, this is a case where we have the three forces acting, and we can take moment either at the end, or we can take moment at the point where the forces are acting. I've always said that take your moment either at these ends or where the forces are acting. Those are the only points where you can take your moment. That means that position that you're going to make, that is a position that you're going to put your pivot. So for me, I want to take my moment where the force 0.5 Newton is acting at. So my moment, I'm going to take it there, meaning I'm going to pivot it there. Now, if I pivot it at that position, then it simply means that 0.5 Newton is not going to produce a force. Now, if I take my moment at this point where the 0.5 Newton is acting, and then assume there is no force tension, only the force of 3 Newton is acting, you will find it is pushing it up. So the body, just a minute, sorry. Let's take our moment at this point, 0.3, yeah. so that I get unbalanced forces, because these two forces are going to act in the same direction, so it will not balance. So if I take my moment at 0.3 Newton, I'll remain with the two forces acting in an opposite direction. So for that case, taking your moments about this point, where the force of 0.3 Newton is acting, you are going to have this force here. If it is acting alone, assume the tension is not there, you're going to have it pulling the body down or in anti-clockwise direction. This one, if there is no 0.5 Newton force acting, it is going to move the body up. So from there, you develop an equilibrium. So from there, we are going to say that clockwise moment is always equal to anti-clockwise moments. Now, because there is no force at the end, so we just consider the two forces because they are the only forces acting. We're going to say the distance from here up to there, which is 60 now, that is 0.6 times the force, which is 0.5, should be equal to now the forces at the moment produced by tension, which is T, times the distance. If this is 60 and this is 30, actually it means from here up to here is also 30. So that is 0.3, and then T will be equal to 0.6 times 0.5 divided by 0.3. That will now give you the tension. So always moment, remember moment also combine the ideas of COG. So always when you're handling the moment, look at the question, especially when it is a meter rule. If you have been given the weight of the meter rule, always consider it is going to produce a moment. But if it is not mentioned, assume it is negligible if the question does not specify. So always consider it. Like the Form 3 question, the meter rule had no mass, or rather it had no weight, therefore there was no idea of COG. Fine. Question, back to your paper. Question. What am I having? Yeah, question 5. Question 5 talks about an aircraft. Now that is a question on a projectile motion. And before I handle it, I just want to review a projectile motion. A projectile motion, what we call projectile motion. Now, a projectile motion is a combined motion that involves both the vertical, either it is moving up or down, vertical and horizontal motion, and both are happening simultaneously at a go. That will be like when you throw, for example, if you are standing some height from the ground, and then you throw, let's say, like a stone. This stone will move, and then at some point it will land on the ground there. So you will see, you threw the ball horizontally. This was a horizontal motion, but now it ended up on the ground, meaning from where you threw it, some height, it fall down. So this is the vertical motion. It is being brought down. Now, with those two, both horizontal and vertical motion at a go, we are going to have the body. For horizontal motion, we usually assume that if there was no force acting on it, this body will forever move in a horizontal with the same velocity with which you started it with. Therefore, it usually moves with a constant acceleration. Acceleration is not changing.
Please,
So
Madam,
actually,
repeat the definition of a projectile motion.
Yeah.
You repeat the definition of a projectile motion. One student is asking.
Oh, projectile motion. We are saying a motion that involves both vertical and a horizontal motion at a go or simultaneously. Both are happening at a given time simultaneously. So is a motion that involves a vertical that either is a movement up or down, and a horizontal, which is from side or from side to side. So now we treat the two motions. The horizontal motions, we know for any motion we always require time taken, t. We need initial velocity, u. We need final velocity. We need distance covered, and we need acceleration. Now, all those, they are values that we usually have. So that is for horizontal. That is a motion in this direction. For the vertical, that is downfall. This is a horizontal. For the vertical motion, still again, you will need time that it requires to start from the highest or the position it was until it reaches the ground. You will require initial velocity with which it left. You will require the final velocity with which it touches the ground at this point. You will require the displacement, and then you will require an acceleration. Now, let's start with the vertical. For the vertical, the body is moving down always because you threw it from some distance. So the force, the acceleration of the body, we usually take it to be acceleration due to gravity. And that is always positive g, which is mostly either 10 meters per second or 9.8 meters per second, depending on what question give you. Because mostly in high school, we use 9.8 meters per second or 10 meters per second. So this one always, every time you're having a projectile motion, it is going to be there. Then the displacement here is this height here, the height from which you threw it. I can call it the maximum height. So this, the displacement is h max. The final velocity, we usually don't have it, so we can calculate it. The initial velocity for a vertical motion, because it was some distance, so we usually take it was stationary. So we usually take the initial velocity for a vertical motion to be 0. And the time taken for it to move all until it reaches the ground is the same time the vertical is going to take. So t is equal for both horizontal and vertical. The time taken to reach the ground is the same time it takes to move in the air. So for both the vertical and the horizontal motion, they are going to be same. Now, so ready for the horizontal we have, now time, and for the initial velocity, usually we are given from the question. Like the question you're going to handle, we have the initial motion, which now this one you usually don't have it, and commonly is the what you're going to calculate. Final is same as the initial because we are assuming that that body is going to move constantly if there was no force of gravity acting on it. So usually that body is not accelerating, it is moving with a constant velocity. So that also tells us that acceleration is 0 because final and initial are equal. You subtract them, you get a 0. So their acceleration always you're going to have it as 0. Then, now the displacement that is from where you threw it to where it fell, this distance here, we usually call it the range. So commonly we refer to it as the range. That is the distance from where you are to where it fell. We call it the range. And usually also it is calculated. So now with that information, we can go back to our three basic linear equations. Remember, the first equation is the equation where we have V is equal to AT plus V is equal to let me just V is equal to AT plus U, or rather U is equal to U plus AT. Then second equation is usually S is equal to UT plus a half AT square. Third equation is v square is equal to u square is equal to u square plus 2as. Now, so those are the three basic equations that we have for the linear motion. So from there, now if it is a horizontal motion, then we can get the final velocity. Now our final velocity, so for vertical motion, if we use equation 1, which is v is equal to u plus at, then we know our initial velocity is usually 0. It will mean that our final velocity here can be found by v is equal to, okay, u is 0, so is equal to at, so that, and a we know is g, so that is equal to gt. Actually, final velocity can be found by gt, as long as you know the time. Now, the S we can use the second equation again, for vertical, H max. So we know S is equal to ut plus a half at square, but u is 0. So we're going to remain with S is equal to a half gt square. So it means that S is going to be found by a half gt square. Now, so with that, basically with that, we can now yeah, so for horizontal, now horizontal, we know if we want to find the range for horizontal, that is S, the displacement, then we can use the second equation. So if we use second equation, we are going to say that S is equal to ut plus a half at square. Now, what we know is that acceleration for horizontal, we said is 0. So if you substitute 0 there, you will end up with S is equal to ut, which if you have u and you have time, then you can go ahead and get your S, or the maximum height. Now, with that, now we can go back to our equation. Now, an aircraft 300 meters from the ground traveling horizontally at 400 meters per second releases a parcel. Calculate the horizontal distance covered by the parcel from the point of release. So that is like if we had the plane is here traveling with some speed, and then it releases a parcel. So we expected the parcel to move with the same velocity, and it is at a height of 300 meters. So like from there, we have H max we have been given, that is 300 meters. And then traveling horizontally, now we have like the initial velocity. So from here, for vertical motion, we have been given S, let me erase this part. We have been given subset S here is given as ut. Now, we have been given S for vertical motion, we have been given S, or the height from which it was released, to be 300 meters. And we have been given for horizontal, we have been given initial velocity U, which is 400 meters per second. So with that, now we know T is the same. S, which we have here, can be given as a half gt square. And we are looking for the S here, which S is given, S here is given as UT. Now from here we can get T alone. From here we can get T alone because we just need to, that is going to be cross multiply, you're going to get T is equal to, if you make T the subject, square root of 2S over G. So that will give you T. And if now we have 2S, okay, let me now use H here. So let's use H, the height H. So let's say this is 2H. Now we have H, we know G, and time is what we are looking for. Now what we are looking for here, the question is looking for this S. So we know S is equal to UT, but T already we have it here. So we're going to say S is equal to U times square root 2H over G. So substituting the formula, put it here, we're going to have S, which is the range, is equal to initial velocity, which is 400 meters per second, times the square root of 2 times the height, which is 300. 300, remember the square root cut off everything, divide by G, which G here we now use 10. That will give you, that is 400 times square root of the square root of 60, and then you will get your value in meters. That was question 5. Question 6, we move to question 6 unless there is a question. Question 6, the figure below shows 2 experiments to investigate energy transfer in water. Name the process by which thermal heat energy travels through the glass. So we have the two test tubes, one wrapped here. This was an ice, and then we have in water, we know ice always, and then we have another one here, and then ice here wrapped in some wire, and this is an ice, and then this is water. Now we are investigating the energy transfer. This one we are hitting at this point. This one we are hitting at this point. Now, if you look at these two, what we know, let's see what happens here. When you hit water according to the convectional current, the molecules at this point is going to gain some energy and then expand. If it expands, then it means that its density is going to be low. So it will rise up, and the cold one that is being cooled by ice will come down. So the water molecule or heat transfer will be spread through. So when the hot water gets here, some heat will be absorbed by the ice, and the ice will melt. So the water is moving by water molecule, water is going to be heated here, or the ice is going to be heated by convection. For this case, if you look, we are hitting at the top. We are hitting at the top, and when we are hitting at the top, the water here is going to be expand, and then thus is going to become less dense. And if it becomes less dense, what is going to happen? It cannot displace the cold water that is being cooled by the ice. So only the water at the top is going to be hot, and the one at the bottom is going to be remain cold. So at this point, we don't expect the ice to melt. So here ice will melt, but here ice will not melt because the convection current cannot flow. That question, if I compare it with a similar question in Form 3, If I compare it with a similar question in Form 3, the Form 3 question was asking, state with the reason which water cooled fast. It was similar, only the apparatus was different. Everything was the same. The question was asking, state with reason which water cooled faster, assuming that the gauge absorbed, the gauge or the wire here absorbed negligible heat. Now, already, which one cooled faster? They were asking which one cooled faster. Okay, for this case, they were not heating. There was no heating. They had just to place some water. So there was no heating here and there was no heating there. And they were asking, now you state and explain which water will cool faster. Different from what you had. Now, always for both the questions, they are using a wire gauge. And the role of this wire gauge, we know, according to anemolas expansion of water, the ice always float, is less denser than water. So ice will float. So the wire gauge, we are using it for this case to make the ice sink. So the use of the role of wire gauge is to make ice sink. So that is what it does. But the wire gauge is a good conductor. So also it is going to absorb some heat. So it absorbs some heat. That is why for the Form 3 question, they are saying you assume that no heat is being absorbed. Now let's look at that and try to answer the Form 3 question, which says that which one will cool faster if we place one ice at the top and the other ice at the bottom. Assume that water were hot. Now here they were using hot water. So they were using hot water in both cases. One you place the ice at the top, the other you place the ice at the bottom. If you look at the two questions, so if you look at now the Form 3 question, you will find that the ice at this point is colder, so it is going to cool the water around it. And if it cools the water around, the cold water is denser, so it is going to move down, and the warmer water is going to move up. So conventionally, there will be a conventional current. If you look at this, the cold water, the ice here is going to cool the water below, and the cold water cannot displace the water above. So at this case, there is going to be no conventional current or transfer of the energy. So we expect this to cool faster than this, because their conventional current will occur, which will make the hot water to move up. But this one here, there will be no conventional current. Okay? Move on. Back to our paper. Give a reason why ice had to be wrapped on the metal. I've said that is to make the ice sink because it is less denser than water. Question 9, that is speed and velocity. That one everybody knows. Now, in the study of free fall, it is assumed that the force F acting on a given body of mass M is gravitational. Given by force is equal to mass times gravity. State two other factors that affect other forces that act on the same body. Now, when a body is immersed in a fluid, like this case here, let's say we have a ball bearing here. So this is our ball bearing, and this is the fluid. Now, when everybody on Earth is going to carry its own weight, so that is always the first force, weight of the body, which is given by mg. When this body gets in contact with the liquid, there is a force it is going to exert down, which still its own weight. And then, because it is inside the fluid, there is going to be an upward force. This upward force, the force we call force of buoyancy or an upthrust. So buoyancy or an upthrust is going to act on that body. That is a second force that is going to act on a body immersed in a fluid. Between the wall of the ball bearing or any body that we have immersed and the liquid molecules here, they are going to be an opposing friction force. And because this is a liquid, this is going to be a friction force, which we call in liquid, we call it viscosity. So viscosity is a force because it is a friction in a liquid, and friction in liquid is a force. Then, because also, okay, there is a force here, but because the body is moving, we assume it is negligible. That is a force of attraction between molecules. But now we don't consider it for this case. So whenever we immerse a body in fluid, we are going to have its weight acting down. We're going to have the buoyancy force, which is going to act up, and then we are going to have the friction force, which acts in an opposite. Because the ball is moving down, the friction force is going to, or the viscosity force is going to act upward. So actually, you will find that for this body to move down, the weight of that body is usually given as the upthrust force plus the friction force. So those were the forces, the buoyancy of the upthrust force, and then we had the viscosity, and then apart from its own weight. So the two forces, upthrust and viscosity. Yes, the next question is still on thermal expansion, and that is we have a container, a glass one. We are heating it gently. Colored water, we have colored water. And then it is cocked. It is cocked and then filled with the liquid. Then the level was here. That was before we started heating. Now on gentle heating, what they are saying is that the volume, the level in the tube here falls. That means it goes down before starting to rise again. Now, it falls before starting to rise again. If you look at that, inside the liquid, we usually have the air molecules. So we're going to have some air molecules inside. So when we are heating, air has a very low boiling point. So when you heat, the air first expands and escape. So it's like we are getting rid of the air. So when the air escapes, the volume, the space it was occupying is going to be taken by the liquid. So we expect the volume to fall. Then as you continue heating, now the water will get to the boiling point and then will expand. And if it expands, then it will rise. So to that question, the reason was air, the solution should be air dissolved in water, expand, leaving space for water molecule. Does drop in volume. Full stop. That gives you the first mark. The second mark now will come with as heating continue. Air, water molecule expand. Water molecule expand. Thus rising in the tube. You can see, always I've said, repeated this several times, that every time you're going to have a question, look at the number of mark. The number of mark should guide you the statement. critical point that you're supposed to carry. So instead of starting with a statement because of the story, that is not necessary. What we need is the key point. Now, from here, we expected you to realize that air, on heating, air usually has a low boiling point. So we expect to see somewhere air expanding. That is the statement. Then it will escape. So once it expands, it will escape, or rather it will leave some space. Then the next point now, the water molecule will expand. So those 2 points. So I look at air expansion, that is a mark, and then water molecule expansion, that gives you a second mark. At least that shows that you know what you are doing. So all that story that you write before getting up to here, I've said it is usually irrelevant. And you can look even also the space that you're given in the question. Yes, the next question is on the COG. That's talking about a y-cyclist. Now remember, physics question, they always don't come straightforward. They expect you to apply what you have learned. And especially with the COG, with the COG, there are usually several questions that can touch on the COG, and then it is just applying the practicality of the COG or application in real life. Now, we know COG, or the center of gravity, determine COG, or center of gravity, determine the stability of a body. It is going to determine the stability of a body. That a body is going to be more stable depending on its COG. And those 2 factors that determine the COG, that is going to be the base area of body, and the second is going to be the height of the COG, or the position from where it is on the ground. Now, if I have these 2 bodies, you will find that the first body, if you just do the normal determination of COG, if you do the normal determination of the COG, you will get, I draw a perpendicular, or a bisector, angle bisector, you'll find your COG is there. If I do for this one, you will find your COG is there. So this is the height of the COG, this is the height of the COG. Now you will find, if you apply exert a force here and exert a force here, most likely A is going to fall, but B will not. There's high chances that B is more stable than A. Now A will fall. First reason, the COG is so high, so the weight is so much above. Then the COG is so high. For the second, the COG is so low. So the height is going to determine the stability there. Another thing that is going to determine the stability of that body is the base area. Now, usually if you drop a perpendicular line from the COG to the ground, if you just give this a small tilt, you change its small angle, you will find that this line will fall outside the base. And every time the line, the straight line fall outside the base of a body, then that body automatically will topple, or it will fall. So if you apply a small force, this line here is most likely to fall. That is, if you just apply some small force here, you will find that that line comes down here, and then it has fallen out of the base, it will fall. But for this case, if you apply a small force, this body will tilt up, and that line still will fall within the base. So you see the body will not fall. So the body becomes more stable if it has a broad base, and then it has the low COG. That is why even most vehicles, usually they have their cargoes usually not on the top here, but they usually have the cargo or the base where we put the bags and all that below, lower the COG. So if we go to the question 12, you will find that a cyclist carrying a load on the bicycle carrier, that is the sitting position for a passenger, a white cyclist will carry a load on the bicycle carrier and not on the sack on his back. Now you see, if you're sitting on the bicycle and you carry it on your back, what you are trying to do is you are raising the COG. So if you raise the COG, the lower the stability. So if you're going to make a bend, there's high chances you're going to fall. But if you put it on a carrier, then the COG will remain low, and then you are likely to be more stable. So the reason for that was because of the if you put the sack on the carrier, the COG will remain low, but putting it on your back, you raise the COG, then you make the body less stable. Question? Think up to there. Any question? Question? Any question? You just carry up your hand. Anybody with a question? Nobody. So if there's nobody, then we can end our lesson there, and then we meet next week. Thank you.
Oh, sawa. Tuonane ni kesho. I'm sorry. There was a lot of inconvenience as we ended the lesson because of the phone had an issue of charging. So see you tomorrow. See you tomorrow. Unless if you have a question, you can ask. If you have a question, you can ask. If you have a question, you can ask. Anyone with a question? Anyone with a question? Sumaya? Abdimarik? Anyone with a question? See you tomorrow.
No, it's a physics question.